Bismillahirrahmanirrahim. We started talking last time about the scalability, and we said that scalability refers to the fact that when we add new devices to the internet, the performance of the existing ones should not be affected significantly. Okay, and we have talked about an example of this. We talked about YouTube, and there are so many other examples like Facebook, and there are so many systems that that try to design the infrastructure in such a way that supports scalability. So when the number of users grow very rapidly, you still can get good performance regardless of the number of users. Similarly, of course, this was like an example just for analogy, but in the network, we need to do that from the hardware perspective. So the devices themselves, when they get added to the internet, they should have a similar performance and consistent performance. Fault tolerance, on the other side, is similar to the scalability in a way, but it's not like performance. It talks about the fact that either I have communication or I don't have communication. So fault tolerance here talks about the fact that if part of the network is failing or is dead or has any problem, it should not affect the end-to-end functionality. So in other words, if I have one router in the university is down or it has any problem, that doesn't mean that the whole network will be non-operational. It doesn't make any sense. So I need to have some fault tolerance, which means that, for example, if this router is down, okay, then automatically and seamlessly, I should right away detect that and forward the traffic through this router to the internet. Okay? So if I'm going this way and then I detect that this router is down, then all of a sudden I go this way and this way. Okay? So this is what we mean by fault tolerance. Okay? Okay. Quality of service. Quality of service now talks about the fact that different users and different types of traffic should have different behavior when it comes to internet operation. What that means is, like for example, if we subscribe to one of the services that Uridu, for example, they provide, okay, we don't necessarily have the same service, right? So I have maybe like 1 megabits per second or 10 megabit per second plan, and you have like, I don't know, like 400 megabit per second plan. We should not have the same behavior and the same quality of service, right? In order to provide this discrimination, and quality of service is all about discrimination, really, even though the term might sound bad, but it is all about discrimination. I should discriminate between the users based on how much they pay, which is a fact. I mean, we cannot get around it. How much they pay and what type of traffic they use. For example, if you use video, okay, I should, as a service provider, give you the quality of service you expect when it comes to video. What that means is, it doesn't make any sense that you have a 10 megabit per second plan, and then you get to YouTube, and then your video pauses every now and then. It's not logical. So I need to design my network in such a way that gives you the quality of service you expect, because you are an important user, you pay a lot of money, then you should get the service that you expect. Okay? But in order for us to do that, we really have to design our network accordingly. It's not that easy. Okay? So I need to give I need to allocate some network resources, and by network resources I mean These routers have to really detect that the incoming traffic is for that user and it's a video. Then it should be high priority. Then I should probably pass this traffic faster than if you were to browse like on a normal browser and you need to do like web surfing or something like that. So for web surfing, if you click on like yahoo.com or something, and then the page, spends like 10 seconds, it's okay, right? So it's okay as long as the page comes up at the end of the 10 seconds, then I'm fine with that. But the problem with video is that it's a real-time thing. So it doesn't make any sense that you're watching a football game, for example, and the guy says goal, and then you don't see anything. It's just the quality of experience will be very bad, right? So you will feel it right away. So and that's not what we need. What we need is to give the quality of expectation that you like. Okay. So that's what we mean by, in that case, we need to discriminate and give different resources from the router perspective based on the fact that this is voice, this is video, this is text, and so on. Right? That was not the vision in the past when they started, the internet or even the telephone network, the landline. They didn't have this perspective. They didn't have this vision that I need to really... So the design of the network was based on the fact that, this is a network for voice. That's it. This is a network for video. So TV, this is a network. This is an example for network for video. It uses some kind of, a totally different technology. And then this is a network for voice. Then it should be landline. The switches are designed in such a way, and so on and so forth. Right? So the only way that you get, quality for audio is you have to have like a dedicated connection. That was the vision in the past. You have to have a dedicated connection, and you have to have a link established between you and the other person on the other side. And this circuit has to be established and dedicated for both of you until the call ends. Okay, so we'll talk about that. So that was the perception. The designers of the networks at that time, they did not have any other perception. But with the concept of quality of service, the main benefit of the quality of service now is that if we can discriminate between voice, video, and text, now we can provide a variety of services on the same network. You see what I mean? So instead of having voice, telephone network, video, the only vision about video is TV, and TV satellites and all of this. And then when it comes to... Okay. All right, so... so this is the conversions. Again, we'll repeat it. So the network conversions talks about the fact that we converge all these services over the same network. And if this network is IP network, then the routers here are smart enough to discriminate between the different types of traffic, the different users, and so on, over the same network. So this way we are getting rid of many technologies in the past that we're not using anymore nowadays. So that's what I talked about. So quality of service. So if you have like voice, and if you have here like some financial transaction, and you have here like web page. So financial transaction is usually very time critical in the sense that if I click that I want to, for example, convert some dollars to pounds or to reals or whatever. Okay, if that click spends like 10 seconds or something, the price might change, right? Or I need to buy some stocks. When I click, if it spends 10 or 20 seconds, then the price of the stock might go higher or lower or something like that. So that might affect the customer badly. So the customer would expect when they just request something financially, it should be really accurate, robust, and timely. Okay, so these are this is one example of the applications that are very, very time critical. Another, of course, example which we talked about is video. Okay, so if you're watching video, it should be real time. If some of the frames got delayed in transmission, the effect on you will be like you see some pauses, and that happens sometimes when you see a video on YouTube or something. It pauses, and if that happens repeatedly, then you start, losing interest. You feel like, it's not working well, so I will try some other time. So that happens because, the routers inside the network, they allocate the resources. So they see, okay, this voice, it has to be the highest priority. And then this is like, for example, the financial transaction could be medium priority, depending on the type of the financial transaction. And then the web page browsing is the lowest priority anyway, because if the user, gets the web page 10 seconds after, it's not a big deal. And then based on that, it takes higher priority packets first, and then medium priority packets, and so on. It might actually serve it in such a way that takes all these high priority first, and then it takes the medium priority second, and then the third. So as long as I have packets here, as long as I have information here, I should serve it first. When that queue is empty, then I get the second one, and so on. Like what happens in the airport. So like sometimes in the airport, they direct you towards, like if you are a GCC citizen, you go this way, okay? And then if you're non-GCC citizen, then you go a different way, right? And then when you go there, sometimes they tell you, okay, so you can go to this person now who is serving the GCC, because there's no GCC citizen lining up at the moment. So it's the same type of service, right? So the effect on the user then will be if you have, like, without quality of service, you have a choppy picture, starts to pause, some of the frames they start to have some pixels which are not showing up, resolution start to get crappy and stuff, so the experience that you get is bad. Whereas if you use quality of service, then the resolution will be high, no pauses, and it's a real time, and you see the video as it happens. So if you're watching like live feed on YouTube, you see the video as it happens in reality, not like 10 seconds or even 1 minute later. So that, as we said, that requires special design from the internet point of view. So we'll learn throughout the course how these things can be done from the network perspective, and what is IP and so on. Another very important aspect that, of course, affects every one of us on a daily basis is security. Security comes with it like privacy. So security here has different aspects. There's network security, there's information security, server security, there's privacy. So my information is being transferred over the internet. When I buy something using my credit card, my information is flowing on the internet. So how can I make sure that this information that's flowing on the internet is actually secure? It doesn't get into the hands of someone who can use it in the wrong way. Okay? So security is also another very important aspect. So that's why routers constitute the core and the brain of our network. It has to be intelligent enough to support all these features: fault tolerance, scalability, quality of service, security. All of these have to be implemented inside our routers, which are the vehicles, or even though they are fixed, but they actually use to transfer information across the internet. Okay. So how do you provide network security? As we said, securing the network infrastructure includes the physical securing of devices that provide network connectivity and preventing unauthorized access. So first of all routers have to have the proper authentication and and secure mechanisms that allows only users who are authorized to access these routers. Because if you are not an authorized person and you get to access a router, you can actually make a serious damage to the entire network, because you can, for example, say, okay, I will absorb all the traffic, and then all the traffic that is coming to this router, I will absorb it and destroy it. So you can imagine the amount of damage that this could happen, that this could cause to the network. Or I will take that traffic and I will send it in a wrong way, send it to a different direction, to a machine of a hacker or something like this. Or so you can make a serious damage if you have the improper access to the router. So this is securing the infrastructure itself, the hardware itself of the network. There is another very important aspect of security, which is content security. Content security. So while the content is on a server, I should also make sure that this content is secure. So if this content has like confidential information or it has important information that should not be accessed by anyone, then I should also have the proper mechanism to secure it. So so this, if for example this content includes credit card information, so not only do I have to make it secure on the server, but I actually have to encrypt it and make it hidden and when I try to transfer it over the internet. Because when I send it over the internet, if it's not encrypted or it's sent like in a form of a code, okay, then someone might get this information and get your credit card information and use it. So all this information has to be sent in a secure manner, and we'll talk briefly about how we can do that. Okay, so remember we talked about quality of service and the discrimination, and from the network perspective, as I said before, the perception in the past that the network is designed based on the type of traffic that flows on this network. So as an example is the public switch telephone network or the landline. Another type of network which uses text, or it deals with text mainly, like our Ethernet or our normal network that we use nowadays. Originally, this type of network, it was designed mainly to transfer information between different computers or between different human beings, but with no perception whatsoever about providing any discrimination on quality of service and so on and so forth. So based on the design of network, to customize or to optimize a specific service or provide a specific quality of service, we categorize the network design into two main things. One is called circuit switched networks, and the other is called connection-oriented networks. The other is called connectionless networks. Okay, so by circuit switched connection-oriented networks, we mean that if I need to make a call from here to for example here, okay, I have to make sure that there is a dedicated circuit. A dedicated circuit, which means that I need to have a line. This line has to be dedicated for this call, and when this switch gets the request for your call, it should establish another line that gets to this switch, and then from this switch to this switch. And this line, okay, should be established at the beginning, dedicate itself to this call during the entire call duration, and at the end of the call it gets dismantled. So this blue line becomes like this one, which means that it's not used for any call. And that's why maybe you're young enough that you did not encounter this, but in the past, sometimes when you make a call, you try to dial a number and then it says, all circuits are busy now, please call again later. I don't know if you have heard. So this means that all these lines are consumed, okay? And because I have to have the circuit dedicated for your call, I don't have any circuit to dedicate for you. So you have to try some other time. I don't have any other option. Why? Because I need to give you a consistent quality, okay? So in that case, I have to give you a dedicated line. Since I don't have any dedicated lines now, you have to wait. This is the only choice, okay? So this is what we call circuit switched connection-oriented networks. A very clear example to that is the public switch telephone network that we used to use in the past, okay? And maybe still some of us still use it until now. So public switch telephone networks are circuit switched connection-oriented networks in the sense that when I dial a phone number, okay, I have to wait for a few seconds, right? This wait time is because the network itself is trying to establish this circuit for you, okay? And that's why, and this setup might take seconds, or in some cases maybe 1 minute or something, okay? So there is a setup time. So there is a setup process that has to happen. So when you dial the number goes to the network tries to establish the virtual circuit all the way to the end until it reaches the other side. If this process is successful, then the other side will send an acknowledgement back that, okay, I have established the circuit, and then you start your communication, okay? When you start your communication, then since you have a circuit, if you imagine with me that you have like a pipe, okay, from the sender to the receiver. This pipe is established. It's physical pipe and established. So when you try to send any information, okay, when you try to send any information, it will first flow through that pipe in order, right? It follows the same route because you have established this circuit prior to the communication, right? So going to that example, when I establish this circuit end to end, all the information will follow through this same circuit. Like nothing will go this way. Okay? Everything will follow through this circuit end to end. And this is good in the sense that the information will follow in order, because imagine if some go this way and some go this way, then some pieces of the information might arrive before the others, right? So you start having some like out of order units of information, and that might cause some problems. The good thing about circuit switched is that since you establish a dedicated circuit, it's just a pipe, and you are transferring all the information in order, and then they encounter the same delay, more or less, because they are not going through different routes or different directions or different paths. So they encounter the same performance, and that allows us to provide consistent quality to the users. And that's why landlines, it very rarely it happened that you make a telephone call through the landline and then it gets like pauses, or you get some disruption of voice or something like this. It doesn't happen unless there is, of course, a problem in the switch itself. But that was one way of providing the user with consistent quality. Okay, so that's one mechanism that we use: circuit switched, connection oriented. By connection oriented, we mean that we need to establish a connection. We need to have a setup process. So we need to have this setup process. This is what we mean by connection oriented. Okay, and this connection has to be there throughout the whole duration of the call. Okay, and then it's a temporary circuit because it gets established physically throughout the call duration, and then at the end it gets dismantled. So that doesn't mean that if I establish this circuit, that, okay, I dedicated this circuit for me forever, of course. Of course, when I end my call, someone else might use the same circuit. If you have any failure in this pass, like for example, if this switch during the call it has any problem, then the whole call gets disconnected. So you have to make the connection again. You have to dial again, and you have to make the connection from scratch. Okay. It's a limited number of circuits, which means that, you know, if this limit, you know, is hit, you get this fancy message that all circuits are busy now. Please try again later. Okay, because the amount of circuits that I have is limited. So that's the circuit switched connection-oriented networks, and that type of network has some advantages and disadvantages. Okay. The other approach is what we call packet-switched connectionless networks. So in this type of networks, I do not establish any connection prior to the communication. Any information from this source, okay, it gets cut into units, or what we call them packets, okay? And then these packets, without establishing any connection beforehand, it flows through the network. It goes through this router, and this router might decide in one instance of time to send the packets this way. It might decide at another point in time to send it this way. There is no connection context. You don't have to wait for a connection process. Okay? So it's clear now that the packets might come here out of order, right? Because they can go through different paths. They take different routes. So they can arrive to the destination in a different order. There is no connection, there is no setup process. So the implication of this, or the consequence, is that if you lose one packet, or if one router goes down, for example, if this router goes down, I don't care. I don't have to disrupt the communication. I can just quickly and seamlessly transfer to this route. If that goes down, I will go this way, without disconnecting the connection, because there's no connection. There's no connection end to end. I don't have to set up a connection. I don't have to terminate it. Okay? But the drawback here is that since the packet flow through the network in a different direction, they might arrive unordered, and this way the quality of experience that you provide to the traffic is not necessarily consistent, or is not fixed, because each packet now might encounter different delay depending on what path you take. Like, for example, if you go outside of your home and you want to get to the university, there are multiple routes. If you go in this route today, you will spend, for example, like 20 minutes. If you go through the same route, maybe tomorrow, you will get a different experience. You will spend maybe more, maybe less amount of time. So depending on the time of the day, and depending on the load on each router and stuff, you may encounter different delay. This is different from circuit switched, where it's like a train. So you can think of the circuit switched as a train. So you are going through the same route from one point to another. So that's why it's very easy for train services to have this deterministic time from the time it takes off until it arrives on the other side, because it goes through the same route. It doesn't get affected by traffic jams, whether there is high load, there is low load, doesn't care, because it always has a dedicated line. Okay?
By connection here, you mean it doesn't have like a specific line? Because the routers are somehow connected.
Yeah, the routers are connected, but I'm talking about the data that I'm sending, the traffic.
Yeah, so it doesn't have a certain, like the previous.
Yeah, the previous one.
So
I don't have to establish a circuit. The packets will go through these routers in one time, and then it goes through different routers on the other time.
So that's why we say connectionless. We don't mean
Yes.
that they're not connected.
No. We don't mean that. No. By connectionless here, I refer to the end-to-end connection between the sender and not referring to the fact that there is a connection between the routers. This is a physical connection. The connection that I'm trying to establish here is a logical connection, which is used only to communicate information from one source to one destination.
It depends on what, like available service or like the shortest way to.
Yeah, it depends on the current load. The router here will decide. Okay, so this traffic should go through here because I know that this router is down, or I know that if it goes this way, then it will be the shortest path at this point in time. And shortest does not have to be the real shortest in terms of the number of routers it passes through, but based on whether here there is a traffic jam, so don't go this way, something like that. So shortest here, it does not necessarily mean the shortest physically. It means the lowest in terms of load. There is less traffic jams, and there are so many things. And when we put quality of service on top of that, then video has to go this way because it's the shortest, the fastest. But maybe data will go this way, and it can play on the internet for some time until it reaches. I don't care, something like that. So that's why we said that this router has to have a significant amount of intelligence to address all these issues. Fault tolerance, scalability, security, quality of service, so many things it has to take into consideration.
What happened to our data that received in order?
Yeah, that's a good question. So if my data is received in a different order now, we have to have a mechanism, okay, to reorder them, which is possible. It's not a big deal, okay? And we'll see how this is done. It's very easy. So if this happens, I can deal with it. But the benefit of having fault tolerance here, because remember that this type of networks, it supports fault tolerance and possibly scalability and quality of service much better than the other one. Here, I can have graceful quality of service to the different, regardless of the load. So if you have this type of networks, you cannot hear the voice, all circuits are busy now. Because, like if this is busy, I can transfer it here. If this is busy, I can transfer. I have different routes. And if this path is loaded, okay, then your experience will go a little bit low. If I need to provide quality of service and I need your quality of experience to be at least this much, then and only then I can tell you, okay, keep your traffic waiting because I cannot accommodate more traffic because I need to guarantee the quality of service of the existing ones, of the existing traffic that is already going through the internet. But when the internet started, the concept of quality of service was not there. Okay, so and that's why sometimes when you transfer a file over the internet, if you try this now, you may get a different. You may spend a different time if you try it maybe 1 minute or 1 hour after that, right? Because the load on the internet is different at every instance of time. So depending on that load, you may spend different amount of times each for each transmission you're trying to do. Okay. So this is a clean comparison between the two types of networks. Of course, for circuit switched networks, I need to have a dedicated circuit. it's a temporary circuit, but it's dedicated during the entire communication, right? And it's guaranteed level of quality of service, which is good. But the problem now is that you have a very inefficient use of circuit. Why? Because imagine that you have a dedicated circuit, you have dialed a phone number, and then you started communicating with the person, and then you got distracted by maybe your son or daughter is playing or something. So you put the phone on the couch, and then you start dealing with it. So the communication now is dedicated for you, right? But you're not using it, right? So that's a very inefficient use of resources, because you are taking resources from the network, yet you're not using it. So, that's exactly the reason why for public switch telephone networks and for our cell phone voice services, you pay per minute, right? That's why. Why? Because your call, spans 3 minutes, 4 minutes. You are, consuming resources from the network for this amount of time, regardless whether you use it or not. So if you open the line and then you go away, well, you'll pay for it. It's your fault. You'll pay for it, even if you're not using it.
So our mobile follow the first one?
Yes, even for voice calls over the cell phone, they use circuit switched connection-oriented type of mechanism. But if you notice, for our data plans, they tell you what you pay per use. You pay per kilobyte or per megabyte, right? Regardless of whether you use it for 2 hours, 3 hours, 2 minutes, 3 minutes. Why? Because this uses the connectionless type. So you are consuming the resources from the network based on the amount of information you generate. So if you use like voice call over WhatsApp, okay, that's different from a voice call over your cell phone, the normal voice over your cell phone. Over WhatsApp, you will pay the amount of bytes you send back and forth, which will be taken from your data plan. If you do like the normal voice call, you will pay per amount of time you spend on this voice call. Okay? Mish, we'll stop here and complete this.